Now that we've talked about reflection and refraction of light, let's talk about the diffraction of light. So what's diffraction? Remember that diffraction talks about the bending of light around a bound, or bending of a wave around a boundary, right? So the bending of a wave around a boundary. So let me just prove to you diffraction exists for light. I have a very strong light source here, right? And notice here, if I do this at an angle, you can see a shadow, right? But what I hope you'll notice about the shadow is at the edges of the shadow, the edges are fuzzy. So there's a dark part in the center and then the fuzzy edge of the shadow. Well, why wouldn't a shadow have a fuzzy edge? Well, a shadow will have a fuzzy edge because of diffraction. Because light is bending around my fingers to go into the part that should be occluded. So let's do some vocabulary for that just so we have a name for it. So there's the dark part of the shadow and the light part of the shadow. And there's specific words that mean both those things. Something called the umbra, that's the dark part of a shadow. And then there's something called the penumbra. And that is the fuzzy edge of a shadow, or the partial shadow as it's sometimes called. Okay? So very simply, the existence of a penumbra proves light diffracts. There we go. So notice here about the penumbra, okay, that when my hand is really close to the paper, the edges are very sharp. The more and more I move my hand out, the fuzzier it gets. Why is that? Well, the more space that the light has after the obstruction, the more time it has to occupy the space where it was blocked out. So that's that. Another application of this is eclipses. So I don't know if you've ever heard about an eclipse. There's the totality of the eclipse, and then there's everything else. The totality is the umbra. So if that's here is the sun, okay, and here's the moon, and here's the earth, drawing not to scale, right? There is a part of this where you have the path of totality. The way this tends to go here is that there is sort of a small cone where that's the totality, but then there's the larger shadow of what that is. And so that would be the path of the partial eclipse, and this is where the total eclipse is, because that's where the penumbra is, and that's where the umbra is. In fact, it was the geometry of looking at the eclipses and how wide these totalities were that gave us a sense of the geometry of the size of the moon and the size of the sun relative to each other, which helped Aristarchus out in figuring out how far away all of these things were from, that the sun was from the earth, the moon was from the earth. So we've known about these things for quite some time. So just a quick thing about diffraction. Now, something I can't seem to get here, but if you actually look at the edges of shadows sometimes, you can see color, right? Specifically, at the edge of a shadow, sometimes shadows look blue tinged. Well, why is it blue tinged? Well, let's remember we said longer wavelengths bend more, right? That's the same thing as saying smaller frequencies bend more. So if you think about it, if I have a shadow and the red is bending more into the area than the blue is, right at the edge of the shadow, where that's going to be the light that was bent the least, and that's why it's going to have that blue or violet tinge, because those are the shorter wavelengths, or the higher frequencies. They're not bent as much away from that edge into the inclusion. And so that's why the edges of shadows will sometimes look colored or purplish or bluish on the edge because of the fact that red bends more than blue does or violet does when we're talking about diffraction. So keep that in mind, that with diffraction, higher frequencies bend less than lower frequencies, which was different than what we talked about yesterday with dispersion, which is a refraction effect, where the higher frequencies were bent more, violet was bent more. So if you see a rainbow, actually, that could be caused by either diffraction or by, diffraction or by refraction. And you know which effect it is, because if the red light is spread out more, that's diffraction. If the violet light is spread out more, that is refraction. So what we're going to do is look at a very important experiment now about the diffraction of light, something called the Young's double slit experiment, one of the most important experiments in all of science. So we're going to watch me actually replicate this experiment in my office, and then we're going to come back to the whiteboard to discuss the math of it.